this, I call it Avogadro's law. If you have two gases that are the same volume, as long as they're at the same temperature and pressure, they'll have the same number of particles inside. And that law was developed, I think, from him doing reactions and finding out the ratios in which things will react. He was kind of building on John Dalton's first atomic theory. And so, yeah, this was a big-time discovery. So what Avogadro was saying was, if you increase the number of moles of gas in a container, the volume also will increase. Remember, the temperature and pressure have to be the same. So Avogadro's law is boiled down to an equation that looks like this. V equals some constant times N. So we've seen three equations. What do you notice about the three? And they're all solving for volume, aren't they? In each case, it's V equals something.
And there's three Ks.
Yes. The three Ks are not related to each other, but they are constant numbers. They're proportionality constants. All right. Now, let's put these three together. And up here, if the volume is equal to, according to Boyle, K times 1 over P, according to Charles, K times T, and according to Avogadro, K times N, then we can put these three equations together, and N times T over P, N and T are both in the numerator, P is in the denominator. If they're all determined and multiplied by some constant, that would equal V.
I remember that equation.
This covers the four variables that affect gas behavior. So these four variables are all kind of wrapped up in this equation. Now, if we take the P and we move it over to the left side, then we're going to have PV equals K times NT. K being the constant in this case. And if we plot NT on the x-axis and PV, remember the P is over here with the V, the PV on the y-axis, then that slope, and I said so down in parentheses here, the slope is going to equal what we'll call R. And you know what R is? Yes? No. The gas constant, right. The constant from PV equals nRT, which is what this says. PV equals K, which we'll rename R, R times NT. And just rearrange that N and R in the equation. Yes?
How do we get V equals K NT over P from the three equations?
This is the first
Oh,
one.
we're just taking this, and putting them all together. N and T are in the numerator, P is in the denominator. So if volume is equal to these three things, then we can put them all together.
Won't the K be the same?
No, the K's are different. Every one of these K's is different.
Wait, so
That's why we can put them all together. If it was just volume equals 1 over P and didn't have a K there, then we wouldn't be able to use it.
oh, the other ones are the same.
Yeah.
The temperature. Okay.
Yeah. So because V is proportional to 1 over pressure, it's proportional to temperature, and it's proportional to N, then it's proportional to NT over P. And that constant of proportionality is what we'll call K. That wraps those two quantities together. So just one other thing about this, and that is the value on R. You remember what R is? 60? Do you remember it?
68.
No. 62.4. 62.4. Now, what's the unit on that? That's when our pressure is in millimeters. And just know, when you get doing the problems, you'll see pressures expressed in torr a lot. So 62.4 will be also used with torr liters over moles Kelvin.
Doesn't this have to be by like a standard pressure?
It doesn't have to be, no.
What Look at
Yeah,
the
it's
equation you could
2.4
only
and then
use
like
this.
1 per D and then like.
The 22.4. 22.4 liters equals 1 mole. That's the only time I use that. Okay, we have other values of R too. Now does it come back to you? What's the other value of R?
180. 180. No, but it's the 1.
Oh, 108.3 or no?
It's 101.3 is standard pressure. Not a 1 point, no.
0.0.
Yes, yes. R is 0.0821.
Oh.
I will admit that the solution guide uses 0.08206. They use 4 sig figs. I'm totally good with 3, so I just keep it at 3. The brain is bigger than mine.
Instead of having just a bigger brain on the left side, just be bigger.
Yeah, I think so. Maybe that was Avogadro's problem. Maybe the left side was kind of impeding on the right side.
Maybe he had a break.
Pushing out of his head. One other value of R. Yes, it's 8 point. Who said that? Do you remember it? Very nice. And what's the unit on that one? It's kilopascals, yeah. Good memory. So yeah, you have these. Do some problems. Get going on them early. I'll just give you a quick overview of the physics ideal gas law derivation. Oh, we have the kinetic molecular theory too. But yeah, with the this is what you'll see tomorrow. Assume that there's one particle inside of a closed container, and it's moving in one dimension, back and forth, just along the x-axis. So we can determine, and look at all that physics, velocity, distance, frequency. Oh man, it's all physics. Katie, you'll be so happy.
I know.
And then we have a force. Oh my goodness, and I see Newton's second law, F equals ma. And then, we're starting to build up to pressure because pressure is force per area. So that's where we're kind of going to start. We make all these assumptions, and the assumptions are good. We have collisions. We have Newton's third law going on. Well, not yet, but the final velocity is the same as the initial if it's elastic. And then we'll put things together doing some algebra. Newton's third law. The particle hits the wall's hitting back on the particle, so it feels that. So yeah, you'll do all this with Mr. Hevel. I see that we're kind of building up to kinetic energy there. You see an mv squared term. So there you go. If you're normal, you're welcome just to stay in the room tomorrow. You don't have to go listen to the physics presentation. All right, my friends, have a nice today and tomorrow, and I'll see you Thursday. Sorry.
Again, Northwestern University Counseling Office.
Do one word one and you do back together for
There's a trade-off, isn't there? Yeah. Oh my gosh. How's it going with Mr. Crawford, your teacher? Is it weird?